Thermodynamics is the study of energy and how it moves, changes, and powers everything around us. It explains how heat works, why engines run, and even how the sun gives us energy. So in this video, we'll break down the basic of thermodynamics and see why it is important in science and our daily lives. So let's get started. So now, let's define what is the second law of thermodynamics. Have you ever thought, why is it that when you leave an ice cube at the room temperature, it begins to melt? Have you ever thought about that? And also, why do we get older and never younger? So, certain things happen in one direction, not the other. It is called the arrow of time. And it encompasses that however area of science. The thermodynamic arrow of time is entropy. It's called entropy. As a measurement of disorder within a system. The entropy is the measurement of the disorder within a system. Denote as delta S, the change of entropy suggests that time itself is asymmetric with respect to the order of an isolated system, meaning a system will become more disordered as time increases. So take note that a system will become more disordered as time increases. So the second law of thermodynamics states that the state of entropy of the entire universe is an isolated system and will increase over time. So the second law also state that the changes in the entropy in the universe can never be negative. It can be positive. It can be positive but never be negative. Also, the second law of thermodynamics can also be stated that all spontaneous process produce an increase in the entropy of the universe. So there are four major players in developing the second law of thermodynamics. So first is Nicolas Leonard Sadi Carnot. So Nicolas Leonard Sadi Carnot was a French physicist who is considered to be the father of thermodynamics. So he is considered as the father of thermodynamics. So he is responsible for the origin of the second law of thermodynamics. So as well as various other concepts of it. So the current form of the second law uses entropy rather than caloric, which is what Sadi Carnot used to describe the second one is Rudolf Clausius. So Rudolf Clausius was a German physicist, and he developed the Clausius statement, which states that heat generally cannot flow spontaneously from a material at a lower temperature to a material at a higher temperature. Which means that the heat cannot flow spontaneously from a material daw nga lower ang temperature paingon sa material nga higher ang temperature. So mao to ang statement ni Rudolf Clausius. The third one is William Thomson. William Thomson, also known as Lord Kelvin. So William Thomson formulated the Kelvin statement, which states it is impossible to convert the heat completely in a cyclic process. So this means that there is no way for one to convert all the energy of a system and to work without losing energy. So the last one is Constantine Karachodori. Constantine Karachodori he is a Greek mathematician, created his own statement of the second law, arguing that in the neighborhood of any initial state, there are states which cannot be approached arbitrarily close through adiabatic change of state.
So today I'll give you one problem about this topic. The first one is a heat engine absorbs 4,500 joules of heat energy from a hot savior and discards 2,500 joules into the environment. A. How much work is performed by this heat engine? B. Calculate the thermal efficiency of this engine. So first, we need to identify the hot and cold energy. So the hot is for 50 joules and the cold one is 2,500 joules. So let's proceed. QH equals 4,500 joules and the QC is 2,500 joules. So W equals QH minus QC is 4,500 joules minus 2,500 joules. So the total of 2,000 joules. So in this problem, you need to um, you need to subtract the heat and cold. So let's go back to the problem. So the total of how much work is performed by this heat engine is 2,000 joules. So in B, calculate the thermal efficiency of this engine. So E equals W divided by QAH times 100%. The E represents the efficiency and the W is the total of joules like Gaina. And then 2000 joules I divided 4,500 joules times 100% is 44.4. The second law of thermodynamics states that the total entropy of the universe always increases in a spontaneous process and remains constant in a reversible process. Entropy, a measure of disorder energy dispersion, naturally tends to increase as system moves towards state of higher randomness. For spontaneous process, the total entropy change of the system and surroundings is always positive, while the reversible process it remains zero. In reality, all natural processes are irreversible, meaning they involve some loss usable energy and overall increase the entropy. This law highlights the directional nature of energy transformations and fundamental tendency of the universe towards greater disorder over time.